This video is brought to you by mywayteaching.com.
In this part, you can see field lines around simple charge configurations. Okay. See, the field lines are in three-dimensional space, but in figure you can see only in two-dimensional, on a plane. And the field lines of a single positive charge are radially outward, as you can see in this figure. And in case of negative charge, it is radially inward. So this is positive and this is negative charge. And the field lines around a system of two positive charges, if you consider, you can see in the figure C here, this is the field lines. This is the field lines around two positive charges, Q and Q. It gives a vivid pictorial representation of their mutual repulsion because like charges repel each other. But if you consider the field lines around two unlike charges, like the figure C, as you can see here, one positive and one negative charge, here the two charges are of opposite signs, so they attract each other. Okay, you can see the mutual attraction between the charges. And these field lines, generally they follow some of the properties. So what are the properties? Let us see. So the first property of the field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. So if there are two charges, then always the field lines, they start from positive charge and they end at negative charge. If there is a single charge, then they can start or end at any point. There is no rule for that. That is the first property of field line. Okay. And the second property is, in a charge-free region, electric field lines can be taken to be continuous curves without any breaks. If it is a charge-free region, then the electric field will be continuous. Okay. And the third property is, two field lines can never cross each other. This is a very important property. Two field lines can never cross each other. If they did, then the field at that point of interaction will not have a unique direction which is observed. Okay, this is a very important property of field lines. They cannot intersect each other. And the fourth property is, electrostatic field lines do not form any closed loops. Okay, these the field lines, they do not form any closed loops like this. This is from the conservative nature of electric field. Okay, so these four are the important properties of electric field lines. Now let us study one more interesting concept, that is electric flux. You just consider flow of a liquid with velocity v through a small flat surface area ds. This is, if you consider this as ds, and a direction normal to the surface that liquid is flowing. And the rate of flow of liquid is given by the volume crossing the area per unit volume, isn't it? That is VDS. And it represents the flux of liquid flowing across the plane. So what is that amount of liquid which is crossing that area? Is there? No, that is nothing but the flux. If the normal to the surface is not parallel to the direction of flow of liquid, that is to V, but makes an angle theta with it, then the projected area in a plane which is perpendicular to V, then we can take it as ds cos theta. So the flux going out of the surface ds in that case will be V n cap ds. So for the case of electric field, we define one more analogous quantity, and the name of the quantity is electric flux. Okay. But one thing is clear, that there is no flow of a physical observable quantity unlike the case of liquid flow. In liquid, there is a physical quantity liquid, but in case of electric fields, it's not physically that the flux is flowing. So in the picture of electric field lines which are described in the previous case, we saw that the number of field lines they crossing a unit area placed normal to the field at a point is the measure of strength of electric field at that point. If you consider this as a unit area, the number of electric field lines which are crossing this unit area perpendicular to the surface, this defines the strength of electric field. That is what we call it as electric flux. Okay. See, we place a small planar element of area delta S normal to E at a point. As you can see, this is a planar element of area delta S and this is E, which is placed normal to E at a point. The number of field lines crossing it is proportional to, yes, it is proportional to E into delta S. Okay. Suppose now, if we take the area element by an angle theta, as you can see in this figure, it is tilted by an angle theta. In that case, the number of field lines crossing the area element will be smaller, and the projection of the area element normal to E is given by delta S cos theta. Isn't it? Here it was normal, but here it makes an angle theta. So the number of field lines crossing delta S is proportional to, in this case it is proportional to E delta S cos theta. When theta is 90 degree, field lines will be parallel to delta S and it will not cross it at all. And the orientation of this area element and not merely its magnitude is important. For example, in a stream, the amount of water which is flowing through a ring will naturally depend on how you hold the ring. If you hold it normal to the flow, maximum water will flow through it, isn't it? And if you hold it with some other orientation, if it makes some angle, then obviously the amount of water which flows through that ring will be smaller. So this shows that an area element should be treated as a vector. So here both this direction is also important. It has both magnitude as well as direction. Then how to specify this direction of area, planar area? So the normal to the plane specifies the orientation of the plane. So the direction of a planar vector is along its normal. See here, in order to consider the direction, we imagine dividing the surface into a large number of very small area elements. And each small area element may be treated as planar and a vector is associated with it. The direction of an area element is along its normal, but a normal can point in two directions. Which is direction do we choose as the direction of the vector which is associated with that area element? But in case of closed surface, the convention is very simple. It's not complicated at all. A vector associated with every area element of a closed surface is taken to be in the direction of outward normal. Okay. You can see convention for defining normal, vector and delta S. The area element vector delta S at a point on a closed surface, it equals delta S into N. Okay. Where delta S is magnitude of the area element and N cap is a unit vector in the direction of outward normal at that point. Now, Coming to the definition of electric flux delta pi through an area element delta S, if you consider, then it is given by electric flux delta pi is equal to E into delta S, that is equal to E into delta S cos theta. So it is proportional to the number of field lines cutting the area element. So angle theta is nothing but the angle between E and delta S. For a closed surface with the convention stated, theta is the angle between E and the outward normal to the area element. Okay. And the projection of area which is normal to E or component of E along the normal to the area element times the magnitude of the area element is nothing but E perpendicular to delta S. And the unit of electric flux is Newton per Coulomb. One thing is the basic definition of electric flux. We can say that to calculate the total flux through any given surface, we should use the equation that we studied just now. The simple way is to divide the surface into very small area elements and then calculate the flux at each element and then sum it up. That gives the total electric flux. So pi is equal to sigma, which is approximately equal to summation of E into delta S. So the approximation sign is put because the electric field E is to be taken constant over the small area element. But this is mathematically exact only when you take the limit delta S tends to 0. So only here the approximation sign. Now let us study another important and interesting concept, that is electric dipole. This electric dipole is a pair of equal and opposite point charges plus q and minus q separated by a distance 2a. So if you consider one charge and another charge, one is plus q and the another one is minus q, if they are separated by a distance 2a, then we call this as an electric dipole. And the line connecting the two charges, it defines a direction in space, and by convention this direction from minus q to plus q is said to be the direction of dipole, and the midpoint of locations of these two, plus q and minus q, we call it as center of dipole. Okay. And the total charge of the electric dipole is obviously 0, plus q minus q leads to 0. But this does not mean that the field of the electric dipole is 0. Since the charge here, the plus q and minus q, they are separated by some distance, the electric fields due to them when added do not exactly cancel out. However, but when we consider much larger distances than the separation of two charges forming a dipole, the fields due to q and minus q, and in that case they cancel out. So the electric field due to dipole, it therefore falls off at larger distance, faster than like 1 by r2. So the first case is the field of an electric dipole. What is this field of an electric dipole? See, the electric field of pair of charges plus q and minus q at any point in space can be found out from Coulomb's law and superposition principle. So using these two laws, we can find the electric field. See, the results are simple for the following two cases. That is when the point on the dipole axis and when it is in the equatorial plane of the dipole, that is on a plane perpendicular to the dipole axis through its center. But if you consider the electric field at any general point P, that is obtained by adding electric fields of minus Q due to charge minus Q and electric field of plus Q due to charge Q by the parallelogram law. Then only we will get the electric field at any general point P. Okay.